Welcome to the class. Dear students, this is the fourth part of the video Orientation and Reactivity in Benzene Ring. In this part of the video, we will see why halogens act as orthopara directors and why halogen act as ring activators. So we are going to prove that halogens are indeed orthopara directors and they are ring deactivators based on allocation of charges or based on distribution of charges. So we are going to just see where the charges are allocated to. Okay, if they are allocated to ortho and para position, we will finalize it as an ortho para director. Okay, and just by looking at the charges, we will conclude. So without wasting much of the time, let us start. Consider the halogen atom, the benzene ring attached to halogen atom as the primary substituent. These are the lone pair of halogen atom. Now this pair of electron is donated here. When it is getting donated here, this becomes a double bond. This carbon becomes 5. That would be very unstable. So this electron pair, it would come here. So the next structure would be like this. Negative charge would come here. The double bond will come here. Halogen atom, it has lost its one pair, so it would become positive. These pairs are intact. Okay, now this negative charge outside the benzene ring is not so stable. It would get here, and when it gets here, the carbon here becomes unstable, so this would come here, right? So the third structure would be like this. The negative charge will be here, there will be double bond here, and this is as same. Now this, as I said earlier, unstable, and when it comes here, this would go here. The fourth structure will be like this. Right? Now this charge, as I have said, is unstable outside the ring. It would come here. When it comes here, this pair now goes back. Now the halogen has got its lone pair back in the fifth structure. Also, one full complete round has taken place for halobenzene. The electron pair which was here now has come here in this structure. So these two are actually the structures of halobenzene, and these are all contributing structures, right? So now the overall structure can be represented like this. This is this thing, right? Negative charge at this position here, at this position, and at this position. Negative charge. One bond is intact, right? The other one is not. Correct? In these and these structures there is no double bond, while in three structures there are double bonds. So that is, I have represented as dotted form, that is half is formed and half is not. And here you go, you can write this and positive charge. So this is the now overall structure. Now the overall the hybrid structure, resonance hybrid structure represents all these structures, right? So the halobenzene is not like this, not like this. At any given time, a halobenzene is a combination of all these structures, and it is referred to as a resonance hybrid structure. So at any given time, it would seem like this only, right? It would be a combination of all the hybrid, all the resonating structures. Now you can see what we have seen here is that a lone pair of electron, okay, has been donated by halogen atom, and that has interacted with the 6 pi electrons of the benzene ring. Correct? So two things we can note here. There are two things that is noted here, that is noticeable here. Number one, these are the main points. Number one, there is an inductive effect. Correct? There is an inductive effect, and that inductive effect is acting like this, upwards towards the halogen atom. The halogen atom is a very electronegative atom. It's a highly electronegative atom. In Mendeleev periodic table, the highest electronegative series is halogen. right? So it's a very highly electronegative atom, so it would try to withdraw all the electrons of benzene ring towards itself. So the minus I effect is towards upwards, it is acting upwards. And there is another effect, resonating effect, resonance effect or mesomeric effect, which is acting downwards. That when the lone pair of electron is donated, right, the electrons are circulated within the benzene ring. So there is a resonating effect which is acting downwards and an inductive effect that is acting upwards. So these forces oppose each other. These forces oppose each other and inductive effect predominates. Inductive effect predominates. In this battle, inductive effect wins. Why inductive effect wins or why it predominates? Because the halogen atom is highly electronegative atom. So ultimately the winning side will be the inductive effect. So ultimately the electron density of the benzene ring would reduce. Electron density of benzene ring will reduce because inductive effect predominates. Why it predominates? Because the halogen atom is so electronegative, it would withdraw all the electrons of benzene ring towards itself. So the electron density of benzene ring would come down. There is no other option. And halogen atom, it would act as a ring deactivator. It is acting as a ring deactivator. Okay. So now we have proven that it acts as ring deactivator. The third point is resonating effect is not dead. Resonating effect is still there. Okay. It is less. I agree, it is weaker as compared to inductive effect, but resonating effect is still there. Okay. It acts downwards, right? So because of this resonating effect on play, there is electron density at ortho and para position. I agree, resonating effect is weak, but whatever resonating effect is there and is in play, that is responsible for the electron density at ortho and para position. Now the electrophile here, if it comes into this reaction system, it would only attack ortho and para position, not with that much affinity, but with less affinity. Okay, it would attack the ortho and the para position. Why? Because ortho and para positions have electron density, even though it is less, but it has electron density as compared to meta position. And why this electron density is there? That is because of the mild resonating effect that is there in halogens. Dear students, this is the reason why halogens act as ortho para directors and ring deactivators. Now in this same video we will see orientation when alkyl groups are present. What we are going to prove here is that alkyl group are wonderful, fabulous ring activators and ortho para directors. How alkyl groups are doing so, we will see by looking at the allocation of charges or the distribution of charges. Let us go through that also. I will draw the structure of benzene ring when methyl group is present as the primary substituents, and we are going to look into it, how it is a wonderful ring activator and how it acts as an ortho para director. Let us see methyl group. So this is the toluene, correct? The primary substituent is the CH3 group. Now what happens here? This CH bond assumes a no bond character. What is a no bond character? It breaks this bond. It breaks this bond. This becomes H plus. And this pair of electron, are you seeing it? Yes. This pair of electron, it goes here. So when it goes here, this electron pair comes here. Okay. So we are going to do it right now. This would go from here. This would come here. And this pair of electron would come here. Fine. This phenomena is called as hyperconjugation or no bond resonance. Okay, so it is going to distribute its negative charge and get involved in delocalization. That would make this stable. Okay, that would make the system more stable. For making itself like this, for extension of the molecular orbital, it would go this pair of electron, it would be shared, right? So we are going to see this phenomena here. Let us see. So now the structure, when this goes, it becomes H plus, and here the double bond comes, so it would become like this, and this pair of electron would come here, and here we go, and H plus is here itself in the vicinity. Now this electron pair is unstable outside, so it would come here, and this, the carbon here becomes 5 in valency, so that would be unstable. This would come here, that would give us the third structure, right? And it is the same here. Like similar case, this would go here and this would come here, and we will get the fourth structure. This is the fourth structure. Now this pair of electron is unstable outside, this would come here, and when this comes here, this carbon would become unstable. So this pair of electron goes back and CH3 is restored. One full round has also taken place, if you have observed so. This pair of electron which was here has now come here. A full one round has taken place, and in between there are these 3 structures. So total now there are 5 structures. 5 structures are possible when is it possible? When this assumes a no bond resonance, or it gives a hyperconjugative effect. Let's draw the overall hybrid structure. Now this is the overall hybrid structure. The overall hybrid structure is represented like this. All the time electron density is at ortho, para, ortho position. Correct? Ortho, para, ortho position. That is represented as such. All the time H plus is in dissociated form, and this bond, one bond is okay, it is intact, the other bond is not so. In 2 of the structures it's not so. So half formed, half broken. That way we have shown, and here we have shown the positive sign. Okay, so here is the resonance hybrid structure. At any given time the toluene will look like this. It would not be this, neither this, it would look like this. It would be a combination of all these structures, because that is what is happening with it inside the structure in a very milliseconds of time. So that is the correct structure and the resonance hybrid structure of the toluene. Now that is not the main point that we are discussing here. The thing is that this structure, these are 5 structures. Let me rub the 5 structures so that we can focus on our resonance hybrid. The thing is that this structure, this here, it has 2 effects. One is plus I effect, correct? It is having a pumping effect. It is having a pumping effect, right? R groups are having pumping effect. This is an R group, it would have a pumping effect. So there is a pumping effect, there is no doubt, and there is another effect which is there, which is that hyperconjugative effect. What is it? Hyperconjugative effect. What is hyperconjugative effect? See, the CH bond assumes a no bond. The CH bond assumes a no bond resonance. Why it does so? It wants to share the sigma electrons. Here there was sigma electron, 2 sigma electrons it want to share with the benzene ring. So it delocalizes those electrons into the benzene ring for extension of the molecular orbital. So when it does so, what happens? You can see it combines with this force. Which force? Pumping effect. Both forces are on same direction, where they are downwards towards the benzene ring. So both forces act downwards, and that would increase the electron density of benzene ring in a big way. Electron density increases in a big way. Both forces become cumulative. That would increase electron density in a big way. Therefore, the R group, that is alkyl groups, are very good ring activators. They are very good ring activators. So first point is proven. The second point is, more, see where the electrons are concentrated. Electron density is concentrated at the ortho and the para position. So not only are they good ring activators, they are very good ortho para directors. Whatever electron density they are able to generate because of these two cumulative forces, they are able to concentrate at ortho and para positions. So they are very good ortho para directors too. Now one thing is there, dear students, the thing is that one needs to have alpha hydrogen atom to show hyperconjugative effect. Which is the alpha hydrogen? What is the alpha carbon atom here? Yes, this is the alpha carbon atom. The carbon atom that is linked to the conjugated system is the alpha carbon atom here. See, conjugated system is the functional group. So the carbon atom that is linked to conjugated atom here is the alpha carbon atom, and these are alpha hydrogen atoms. So more the number of alpha hydrogen atom, more will be the hyperconjugative effect and more will be the chances of higher electron density in the benzene ring. Therefore, for this very reason, the reactivity, I am going to show you the reactivity. This thing, CH3, toluene, no, this thing, it would be more reactive to than this ethyl benzene, right? And that would be more reactive than this isopropyl benzene, right? And that would be more reactive than, what is this, tertiary butyl benzene, tertiary butyl benzene, correct? So toluene would be more reactive than ethyl benzene, which would be more reactive than your isopropyl benzene, would be more reactive than tertiary butyl benzene. Why? Because here there are 3 alpha hydrogen atoms available for hyperconjugation, plus it is having it is having pumping effect. So both these effects are here. Here pumping effect is there, but only 2 alpha hydrogen atoms are possible. So the chances of hyperconjugative, the donation of hyperconjugation towards electron density increase is lesser than this. Here there is only 1 alpha hydrogen atom, so the chances of the contribution of hyperconjugation towards the electron density of benzene is more reduced. Here there is no hyperconjugative effect because there is no alpha hydrogen atom here. So there is only plus R effect, there is only the pumping effect, plus I effect, the pumping effect that is in play. So hyperconjugative effect is not seen here. The electron density is solely dependent upon the pumping effect of the alkyl group here, right? It is not so here, right? Here both the forces are involved. Pumping effect is also involved and hyperconjugative effect. Here pumping effect is involved, hyperconjugative effect is involved, but hyperconjugative not more than this. Here hyperconjugative is less than this, pumping effect is of course involved. So the rate of electrophilic aromatic substitution, here it is the highest and here it is the lowest. These are in between, correct? So this is the highest, after that this, after that this, and lastly this. So electrophilic aromatic substitution reaction would decrease in this manner, right? One more thing that I want to say to you, that consider this is tertiary butyl benzene. Now if an electrophile attacks, an electrophile will attack only owing to the plus I effect. When it pumps the electron density increase, then the electrophile will attack at ortho and para position. But ortho product is not formed. Why? Because there is steric hindrance here. So only the para product will be formed in this case. This is because of steric hindrance at the ortho position. Dear students, this is why halobenzenes, when halogen groups are attached to benzene, it acts as orthopara director and it acts as ring deactivator. And this is the same, and this is why, and we have seen how alkyl group, when it is attached to benzene ring, it acts as a very good ring activator and a fabulous orthopara director. All this we have proved seeing only the allocation of charges or the distribution of charges when resonance structures are drawn. I hope you have understood the class. If you had liked the class and if you have understood it, please do not forget to subscribe this channel. Thank you very much.